I'm Mark Swendsen, the Chief Revenue Officer for Form Bio. I know that I'm standing between you and lunch, so like Henry VIII said to his wives, I won't keep you very long. A little about us. Form Bio is a cloud-based platform for combining data science and bioinformatics. We're headquartered in the US. We have about 50 people. Half of them fully have advanced degrees in disciplines like biology, bioinformatics, and data science. Our focus is on gene therapy companies to help them address their toughest challenges. One of the toughest challenges that we see for gene therapy companies is manufacturability. From that perspective, gene therapy companies have the opposite problem of small molecule companies in the sense that small molecule drug manufacturing is pretty easy, but they don't know if it will be effective, where in gene therapy companies, we know generally it could be effective if we can make it manufacturable and safe. We think that these challenges are actually designed into the product, and these challenges are creating wasted costs, safety indications, and high COGS. McKinsey recommends using data analytics and insight to actually solve these operational challenges, and that's exactly how I want you to think about Form Bio. We are your Sherpa to go up the mountain of data analytics. This is Gartner's analytics ascendancy model, and you can see here on the initial stages, it's really about providing just descriptive and diagnostic analytics before you can provide the insight and foresight of predictive and prescriptive analytics. From that side, we have a powerful solution for diagnostic and descriptive analytics. We have a variety of workflows that allow us to provide a description of what you have and why you have it. In fact, we're partnered right now with PacBio for being their bioinformatics solution for all of their non-human AAV QC workflows. We have point-and-click capabilities, a beautiful graphical user interface, and a dynamic series of reports that allow you to understand what it is that you're manufacturing. But maybe more importantly, we provide predictive and prescriptive analytics on top of that using our machine learning models. In the traditional trial and error A/B testing, actually doing manufacturing can be measured in months before you can actually get returns. On the Form Bio side, we can change that to days. Using our Form Bio deep form machine learning, think of this as a bioreactor simulator, we can actually give you a yield dose prediction for your therapeutic. On top of that, we can also write prescriptive analytics around optimizing those by doing codon substitutions and analyzing secondary and tertiary structures. So let me give you an example. We're working with a variety of CDMOs and gene therapy companies, but one gene therapy company in particular was really struggling with their replication and packaging for AAV. They saw this as being a hurdle for their being able to go to market with certain indications. In fact, they had 4 indications, and they were all standardized on the same AAV9 capsid, but they had wildly different results in terms of truncation and contamination. We help them by actually taking their information and running it through our machine learning model. We have a baseline optimization for optimizing codons and detecting CPG islands. But importantly, we found that there was a need for an enhanced model for predicting secondary and tertiary structures inside the solution. Our machine learning model is a large language transformer model. We trained it on primarily PacBio long read data using thousands of segments, not only from our customers, but also from the public literature. Specifically, we found that what we're used to calling normal DNA is bDNA, and we found that in a variety of cases, the non-bDNA, zDNA, hairpins, cruciforms, slip structures, triple-stranded DNA, a lot of these were responsible for unique things that are happening inside the manufacturing. What's counterintuitive is that some secondary structures allowed for stability and helped in terms of the promotion of the expression in the gene, and some actually led to truncations. You can see here that we were able to map truncation events with very specific secondary and tertiary structures where roughly 110 to 130 base pairs away from that secondary structure, we actually saw these truncations happening. We were able to predict, modeling this, both the propensity and the magnitude of those truncations. Let me orient you on this graph. This is, the top graph is one for the propensity of secondary structures, and you can see those expressed as points in the graph. And below, you can see this is a logarithmic scale of the truncation propensity. The blue in this coding region that we're highlighting is the original. The orange below it is the optimized sequence. So we were able to not only optimize the coding region, but also able to model swapped promoters. In fact, this last week we had another publicly traded gene therapy company gave us a series of 9 viable promoters that they wanted to use with their construct. We were able to hot swap all of them and show them the manufacturing predicted yield. In these cases, we were able to show an increase in full reads by almost 20% and a decrease in truncations by nearly 70%. The ability to actually create higher yields in the manufacturing process allows you to skip iterative cycles by months. It allows you to reduce the safety indications by having more full reads. It allows you to increase your margin and decrease your costs so you're more competitive in the future market. I have a variety of people here. Our booth is just outside this door. I've got Dr. Alpha Diallo, raise your hand, Alpha. And Heather Bell, raise your hand, Heather, if you're looking for people to chat with. But let me pause here for questions or comments or insights or insults. Yeah. Speak up a little bit, sorry.
Machine learning, I'm not very familiar with what that means, but I assume there's a bank of data that you're digging from. What is that?
So his question is, what is your data for machine learning? And I think the underlying supposition in his question is that machine learning gets better with more data. And so being able to get enough data is kind of a critical problem. So we've actually gone out, we're working with a variety of academic institutions, Harvard, UMass, UT Southwestern, getting all the publicly available data. We're also working with all of our customers in terms of their data, and PacBio themselves are providing the data. So the data we're using is that long read AAV sequencing data, but each data set is broken up into thousands of samples where we're able to see those truncation events happening. So it's not just a data set, it's actually kind of fragments of data sets that are also valuable to us. Does that make sense? Other questions? Thank you, ladies and gentlemen.